So next presentation title is All-in-One RISC-V AI Compute Engine for Software-Defined Everything. Presenter is Mr. Volker Politz. Mr. Politz, he is a Chief Sales Officer, Semidynamics, Spain. 日本語でやります。講演タイトルは All-in-One RISC-V AI Compute Engine です。プレゼンターはスペインのセミダイナミクス社チーフセールスオフィサーボルカー・ボリッツ様です。So, Mr. Politz, would you start?
If I can get this to work, then yes. Let me see.
Yeah, you have 20 minutes. So when 50 minutes passed, I ring a bell.
Okay.
Five minutes left.
Okay, I'll try to operate this. So thank you very much. Thank you for having me. Thanks, Shumpei-san, to invite me. I'm happy to be here today.
Yes.
After so long time.
Would you come close to the microphone?
Okay. Okay. So one more time. Thank you for having me. Happy to be here. We're from a Spanish company, and my title, as he said, is the All-in-One RISC-V AI Compute Engine for software-defined everything. We have today heard a lot of. I can't. Okay. So sorry. So Semidynamics is a Spanish company. Strange enough, I worked a long time for Japanese companies, so my Japanese is better than my Spanish. But I'm a German guy, and I'm going to speak in English today. 日本語わかりません。とても少し。Anyway, what I want to say about our company, we're a Spanish company based in Barcelona and founded 2016. We're a 100% European supplier of RISC-V IP. And our specialization is actually in customizing to our customer needs, customizing and configuring it to the needs of our customers. Okay, so I'm really happy to hear that so many people talk today about how RISC-V is used in AI and how it's supporting AI. And of course, we are the same, right? And what you see here is a typical AI SoC architecture. You know, we have a number of CPU cores. We may have an NPU and maybe something like a GPU for the activation. We are very happy to support any RISC-V project in the 64-bit in order, out of order domain, like the green stuff. But people come to me and say, how can you match the green stuff, these CPUs, and help me to communicate to the rest? We think that is maybe not the perfect thing. Because in this picture, you have 3 software stacks. One for the GPU, one for the NPU, one for the CPU. Managing this thing, the traffic between those 3 is very DMA intensive and very not easy to program. And of course, what you're introducing is high latency and the power consumption through these transfers. Then we have a replication of SRAM buffers, caches, and of course, data copies between those. And if you want to scale this one, it's typically not balanced. So we believe there is a better solution to this because it's also not future-proof. As soon as you have this one, next generation, you may need to change the NPU. You get a whole new tool chain for it, or the GPU. And we think RISC-V is offering one more level up of scalability to handle this. If only this worked better here. Excuse me. Okay, so what we are suggesting is that we are merging those parts using the RISC-V opportunity into an all-in-one compute element. Instead of a CPU where you used to add an FPU, now we are having a vector unit, a tensor unit, and a RISC-V core, and all in one as an element. And what that means is you now have a single software stack, no longer 3 tool chains, single chain. Then it's DMA free because it's all an integrated single thing. It has 0 latency and offers lower power because you don't have to transfer data between these parts. The cache size can now be optimized in size. And if you want to scale, well, it's very easy to make a balanced scaling. And it's very future-proof for AI because it's entirely software programmable. So how does this look? So this is an example of our standard RISC-V out-of-order core. And if you want to add the vector unit, as you can see, the instruction flow comes from the decoder now to the vector unit. And then if you want to add a tensor unit, it's all programmable, respectively selectable. It comes through the same chain. Excuse me. And the key point here is that the vector unit and the tensor unit work off the same register file. It means if one of those guys has a calculation result which needs to be transferred somewhere else, there is no transfer. It already sits where it needs to sit, and you simply do the next instruction. So I talked about doing AI on this thing. So what do my customers say when I say this? They say, what software stack do I get? Because obviously when you do NPUs, and I sold NPUs, they're asking, what's your tool chain? The next thing is, can I run today AI models on your IP? How about Transformer, right? Can I scale your solution? And can I run models which come out next year? As you know, it's moving very fast. How about 3 years from now? Now, in order to do this, I want to address the question number one. We decided to focus on ONNX. Why? Because it's open source, and very big guy is behind it, namely Microsoft, and we are anticipating it to not go anywhere anytime soon. So regardless of what you do from here, if you program ONNX, you're pretty much on the safe side. And as you know very well on this picture here on the right side, you see different runtime providers, execution providers. And of course, those exist not only for our IP, but for everybody. It means the chance of you having something running somewhere and running it on our IP is very high. So the next question is, how do you deal with very modern AI? So we've chosen to just see whether we can actually do what we say, running Llama 2 with 7 billion parameters. So what we used is our CPU, plus for this test, a tensor unit of only 1 TOPS here in this case, and a vector unit of 128 GOPS. This is basically what the result is. What you see here is on the left side, if you use the scalar only, then the dominating thing here is the matmul, the matrix multiplication. 99% of all the time, it's just doing this, and activations are 1%. If we switch on just the tensor, then this 99% goes down to 20%. Already we have a 5x speed up on that one. However, the rest is still very complicated and very heavy loaded. And what you see on the right side, if we apply this software to switch on the tensor unit and the vector unit, now what you see is there is almost a 5x speed up from having the accelerator or not. And you can see that matmul is running on the tensor unit and activations on the vector unit. It's a very nice balance between the two. Meaning if you were to go and double the NPU, you lose this ratio and you lose the optimized loading of this IP. So we think this is a very good example of running a very modern workload on a RISC-V IP. And the key point is how can we scale? Now, the way we are scaling is, as I said earlier, our IP is very, very scalable. That means you can select whether it's a 1 TOPS or 2 TOPS or whatever, or a number of GOPS on the vector unit. There are also other configuration options. And the proposal, obviously, we are making is not take T8 and V128, but do the balanced scaling, so to keep the ratio between the two, to keep this thing optimally loaded. And what you can see here is, like in S&P Linux, it's not now a CPU core, it's now a number of balanced processing units to scale. So you can do any of those, any number of those scaling, and it will run under the Linux, for instance. So, question is then, where is ONNX runtime? Well, it's on this core. And yes, we do appreciate and we do acknowledge that there may be systems out there where the central CPU is not RISC-V or is another RISC-V, which is like the green portion here. And what we then add here is an AI engine. We are replacing a very an AI engine, an NPU with a very modern IP, and then the ONNX runtime runs on our RISC-V core. So the question is, how future-proof is this? Well, in this particular case, everything we do, vector and tensor, i.e. GPU and tensor, is controlled by RISC-V instructions. And this RISC-V core has the full if-then-else recursion capability, i.e. Turing complete, we call it, right? It means if the model can be expressed in ONNX, we can run it. And any software which fulfills this if-then-else recursion capability can run on this element. So, I think I'm very fast here, but anyway, our customers' concerns were what software stack do I get? We think we solved that. Can I run today models? Yes, we showed Llama. Can I scale? Yes, we can. And can I run future AI models on this IP? Because they are buying something now and want to make sure that the hardware is running in 3 years from now. So we think we've solved all these customer concerns. And we heard from my colleagues here that they have 10 customers in Japan already. I don't have any customer in Japan because it's 64-bit out of order, modern thinking AI, so please come talk to me. Now, there is one more thing. I just talked about Llama, but the next thing is, what is it, KAN? I'm not sure everybody who is talking about things here is ready. Yeah, we think we are. I think everybody knows that KAN stands for, I don't know, Kolmogorov-Arnold networks, which is basically all FPU multiplications and no matrix multiplication. You can run this immediately on such an IP. That's it from my side.
It's short. We still have more than 5 minutes.
Yeah, I know. So any question, welcome.
Okay. So thank you very much, Mr. Politz. Very interesting presentation, I think. はい、ご質問 Q&A ぜひどうぞ。あちらの2列目の方。
Thank you for a nice presentation. I know that you're going to put, say, big building block like a tensor and also GPU into your building block, and then what you can. I'm sorry, I'm not fully understand what you say, but if you can represent the algorithms in ONNX, basically you can run it on your chip. Is that correct?
Yes, it's IP, yeah, but yes.
But if, say, for example, the problem size exceeds what your chip can accommodate, maybe you still need to move back and forth the data with other chip or other building blocks, something like that. What do you think?
Good question, thank you. So first of all, I want to make sure there is no misunderstanding. We're an IP company, okay? We're an IP company. So our customer take this IP and make a chip, right? 1 core, 4 core, some customers talk about 128 core in a data center, like this, right? That's number one. So, and the way they design the chip is up to them, right? So in our case, we are actually proposing to have a minimized cache, right? Of course, some customers say, no, I want the local cache and the private cache or something, each block element. They have the freedom to do so. We are not restricting this. I want to, however, thank you for asking, point you to this little thing called gazillion on the bottom. Yeah, not really my theme today, but I want to make sure everybody understands, okay? Gazillion is designed to handle cache misses up to 128. The assumption is that if you have a big image for AI processing, which is in the DRAM, right? The cache cannot be big enough to handle 7 billion parameters. You will have cache misses, okay? So typically you can handle 10 to 20. We can handle up to 128. And if the DRAM transfer time is 100 cycles, you will never run out of data. This thing will always be busy. Every other solution like this will sit with the best core mark in the world, will sit there after 20 misses and wait for the DRAM data.
So you can do something like a pipeline manner.
Yeah, so this is, we can handle, we basically can hide this latency and keep the cores running all the time. That's how we do this. However, again, it's a choice of the customer. And I will say it requires a little bit of extra area. And if the customer says, no, I have very big caches on each core, then we can minimize this one. It's a configuration option.
I see. But if, say, the plan of the customer changed after choosing the model of your chip, maybe they are going to have hard time.
Yeah, the key point, this is a RISC-V instruction, basically, right? There is no private instruction. What happens in all these current designs is that, for instance, this one, right? The NPU is perfect, but they cannot do activations. They need the GPU, right? So next the chip is coming, or next thing is coming, this is no longer good, right? And maybe you need to change the design, and then you have the problem of the NPU comes with a new instruction set and a new sort of a tool chain, right? So then in this case, you have to do everything from again. In our case, if it's ONNX, you just run it because we provide the runtime provider. It will directly run with the RISC-V instruction set. And by the way, one more comment. If somebody says, I need to touch this and want to make my own software, you can, because you know it's RISC-V, it's visible, right? Whereas in other such a thing, you never see this instruction set. You never see it for the GPU, and you never see it for the NPU. It's proprietary, and you will never see it. Our case is this, everything is RISC-V.
Right.
I hope this answers your question.
Okay, can I ask just one more question? Okay?
For me, okay.
Yeah, you can ask one more question. So.
You said, the tensor units, vector units, they use the same register file so that you don't have to move data between these two different units. But it looks like the structure of the register file is going to be very complicated, or your wiring between the register file and the unit looks like a spaghetti.
No, it's not spaghetti. This is just implementation, a very clever implementation of a RISC-V specification. There is nothing strange about it, right? Okay. Anyway, you know, we also invite our customers to log in remotely to our FPGA and try count the cycles.
I wonder if you have some technique to handle that complicated. For me, it sounds like a complicated wire.
Gazillion is definitely complicated, but that's something that the sales guy doesn't really talk about, right? We can arrange a meeting with our engineering people.
Thank you very much.
You're welcome. Okay.
Thank you. So, any other questions? それではよろしいですよね。Okay. So, let's close the presentation. Thank you very much.
Thank you so much.
じゃあ、川瀬さんです。